Good morning. Good morning and welcome back. I hope you all had a wonderful spring break and enjoyed some time off. So now it's time to get to the business. So remember, our second midterm exam will be on the next, the Friday after this week, the next Friday. So for today's lecture, I will start with a short review because it has been a while since the last time we met. So I will spend about 10 minutes to have a review of what we learned from the week before the spring break. And then we will continue with chapter 6 and 7, part 2 of the chapter 6 and 7. Okay? All right, so let's look at what we learned before the spring break. So we are in chapter 6 and 7, and we combine these two chapters because both chapters focus on the external flow, the flow outside an object. And we are interested in finding the convection heat transfer coefficient H. So we want to know how do we calculate H when we have different configuration. And last time we discussed a flow of a flat plate. So this is the configuration of a flow of a flat plate. And to find the H, it depends on the flow Reynolds number and as well as the Prandtl number. Okay. So H is a function of Reynolds number and the Prandtl number. And also H can be related to a dimensionless heat transfer coefficient. We call it Nusselt number. Multiply K over X. So instead of finding H, we will start to find the Nusselt number first, and then using this relationship to find H. Okay? So this is one of the important relationships which allow us to determine H. And to find the Nusselt number, we need to know the Reynolds number as well as the Prandtl number. The Prandtl number is a property of fluid. Reynolds number depends on the coordinate x. Okay? So it's a function of x. So here is the characteristics for the convection heat transfer coefficient H. At the very beginning, so near the edge of the plate, the heat convection coefficient is extremely high, so it starts at a very large number. As x increases, it starts to drop up to a critical length, x sub CR. This is where the flow transitions from laminar boundary layer to turbulence boundary layer. Okay? So that's a critical coordinate. And once flow becomes turbulence, it promotes heat transfer. So we will see a jump of H. So H jump to a much higher Reynolds number because flow is turbulent flow. And we know turbulent flow is chaotic. It's help mixing it helps the mixing as well as help the heat transfer. So again, as X further increase, we see H start to drop. So that's the characteristics of H with respect to the X. So as you can see, in order to find the H value, we need to know what type of flow, whether the flow fall into the laminar boundary layer or turbulence boundary layer. So if we need the local value, the H at the location X, we need to know where this location X, whether it's here or here. Okay, so that can be done based on the calculation of Reynolds number. If Reynolds number is less than the critical Reynolds number, and typically for a smooth flat plate, that's the critical Reynolds number is half a million. So if the Reynolds number is less than half a million for a smooth flat plate, then flow is laminar flow. So we use this formula to calculate the Nusselt number. If X is in the turbulence boundary layer region, then we use this equation to find the local Nusselt number. And if we need to find the average Nusselt number, so this is the local, that's the notation where you add a bar to indicate the average between 0 and X. Okay. So let's say I want to find the average Nusselt number between X equal to 0 and X. Okay. In this case, I need to know what type of flow above this length, whether it's pure laminar or it's a mixed flow. So for the drawing I have here, the flow above this region include the laminar part and the turbulent part. So that's where you need to use the mixed flow correlation. So you will need this equation for the mixed flow. So the takeaway message is if you need to find the local edge, you will not need this equation. This equation only applicable to the case when you want to find the average edge. Okay? So that's only for average edge. For the local edge, it's either a laminar or turbulence. You don't have the choice of a mixed flow. Okay? So that's a very important concept. So that's what we learned last time. Flow over a flat plate. And the calculation is quite straightforward. Once you know the type of flow, you just pick the formula from this table and find the Nusselt number. And then you determine H using the Nusselt number multiply K of the flow divided by X. K has to be the thermal conductivity of fluid. Today, so next, the following will be the new topics that we plan to cover today. So we move to the second configuration. So we did the configuration of a flat plate. The second configuration is a closed flow over a long cylinder. So let's first clarify under what condition we can claim the cylinder is a long cylinder. Okay. So for a cylinder, its diameter is d, and the length, I say that's L. In general, if L over D is larger than 10, so the length is about 10 or more times of the diameter, then we can claim this is a long cylinder. And the end effect, the cylinder has two ends, the top end and the lower end. The end effect can be neglected. We only need to consider what happened at the side surface of the cylinder. So that's the concept of a long cylinder.
Excuse me.
Yes.
Can you scroll up a bit? Can you scroll up a bit?
Scroll up.
Yes. Okay. Yeah. For the Nusselt number, it says that it's equal to hx times x over k, but my template says that
Yes.
it's. Did you change?
That's a typo. So that's why I I highlight use red color.
Okay.
Please correct it. If you have a template, please correct it. It has to be x over k. Okay. Thank you for reminding me that. Okay.
Okay.
Yeah. So this is the correct relationship. Okay. So for closed flow, so that's a long cylinder definition. Okay. L over D had to be more than 10. Another concept is about closed flow. What is defined as a closed flow? Closed flow is a flow that is perpendicular to the cylinder. Okay? So the key word is perpendicular. The flow velocity direction has to be perpendicular to the cylinder, not parallel to the cylinder. So that's so-called closed flow. And remember, our objective is to find the convection coefficient H. And the first thing we need to do is to find the Nusselt number. Nusselt number is a function of Reynolds number as well as the Prandtl number. So we need to determine the Reynolds number first. And this is a formula to compute the Reynolds number. As everyone knows, there is a reference length need to be selected when we calculate the Reynolds number. And for closed flow of a cylinder, we choose the diameter. It's not L, it has to be D, the diameter, okay? So for this lecture, the formula, we gave you the formula. The only thing you need to pay attention is these small details. How do you choose the thermal property? That's one. How do you choose the reference value? For example, how do you choose the reference length? For a long cylinder, it has to be the diameter. Okay, I'm sure for some, it's kind of boring because I repeat so many times. But still, I'm pretty sure some of you will make mistake. Okay? So you calculate the Reynolds number, and then based on the equation that I will present later on, you find the Nusselt number, and then you find the average H from the Nusselt number using this relationship, A over D. So again, this is no longer X, it has to be the diameter D. So that's a relationship. And for flow over a cylinder, as well as the third configuration, which is the flow over a sphere, we only have the average heat transfer coefficient. So we only have a coordination for the average Nusselt number. Okay? So we don't have the Nusselt number. Okay. So if we look into the flow characteristics behind the cylinder, so let's look at the top view. So if we look at the flow from the top, this is what we see. Okay? And I actually have a better view. I just found a better view from the internet. Okay, so we have a flow from the left side move toward to the right side. And that's a stagnation point where velocity is zero. That's a so-called front stagnation point. Okay, so this is the terminology introduced in fluid mechanics. And then you actually have a fairly thin boundary layer. It's called the laminar boundary layer. It starts with a very thin laminar boundary layer. And at a certain point, the flow will start to separate, which means you will see the backflow. You will have a negative pressure gradient, so partial P over partial X or partial X. X is the coordinate along the surface, okay, become negative. So flow being pushed forward. So you will see this is the backflow. That's where the flow starts to separate from the surface, and we call that separation point. And the condition for the separation point is when the pressure gradient becomes negative. And the streamline will leave the surface, so now you will have a streamline away from the surface. And eventually the flow becomes turbulence. You will see these eddy, we use this sign to indicate an eddy. How do we define an eddy? What is an eddy? An eddy is a spinning motion of fluid element. A fluid element that spin around, that's so-called eddy. Okay, so we have this spinning motion, and that's a turbulence region, and we quite often we call that wake region. Okay, so that's a fluid mechanics part of the flow of a cylinder. And unlike flow of a flat plate where the Reynolds number had to be extremely high for flow to become turbulent, in the case of a flow of a cylinder, the Reynolds number at a few hundred, order of a few hundred, that's the condition for flow become turbulence. So if you have a Reynolds number equal to a few hundred, the flow is already turbulence. It requires much smaller Reynolds number for flow become turbulence. So that's why most of application for flow of a cylinder is a turbulence flow. Okay. So that's what we learned in fluid mechanics. But let's get back to our interest. Our interest is to find the heat transfer coefficient. Okay? And as I said, we calculate the Reynolds number and use the Reynolds number to find the Nusselt number. And the formula given here, the first one is so-called Hilbert correlation. So all these correlation is based on the experimental study. So we usually call it empirical correlation, and it's derived from the experiment. Yeah. Nowadays, with computational fluid mechanics, we can derive this correlation based on the numerical simulation. Okay? But in the past, these correlations are mainly derived based on experimental data set. Okay? So this Hilbert correlation is very simple. It has been around for 80 years, I believe. And it's still has been used quite often. So it's still a very good correlation. And if you look at this correlation, there are two constants. One is the big C, the other is the little m. And the Prandtl number is 1/3, okay? And that's a typical case. We know Nusselt number is a function of Reynolds number and the Prandtl number. And the Prandtl number, in most of correlation, you will see the Prandtl number will always come up with 1/3. Now, let me try to convince you using the result from uniform flow of a flat plate. Okay, you see this is a table for uniform flow of a flat plate. You see 1/3 here, you see 1/3 here, you see another 1/3. Okay, so when if you in the future, if you work on finding a correlation for certain configuration, you may want to try Prandtl number of 1/3 because that's a typical relationship for Nusselt number and the Prandtl number. Okay, so that's an important observation. And to choose the C and M, it depends on the flow Reynolds number. So you calculate the Reynolds number and then go to table 7.2 to pick up C and M, and come back to this equation to find the Nusselt number. The second point I want to make is when you evaluate the fluid property using this correlation, it had to be the film temperature. Okay, so it had to be film temperature. The property is evaluated at the film temperature. The third point is there is a limitation for this correlation. It requires the Prandtl number to be greater or equal to 0.7, and that's because the experiments Hilbert did is based on air, which has a Prandtl number of 0.7, water, which has a Prandtl number of about 7, and oil, which has a much higher Prandtl number, a few hundred. So he didn't use any gas with a Prandtl number below this 0.7. So that's why he put a limitation. But very likely, this correlation is still applicable for Prandtl number below this 0.7. So, if you don't have other choice, you may still use this correlation in case you have a fluid with a Prandtl number lower than 0.7. Okay, so that's the first correlation. For cross flow of a cylinder, we have quite a few, but in our textbook, it provides 3 correlations. So the first one is a Hilbert. The second one, Zokskis correlation. It's a little more complicated compared to the Hilbert correlation. Okay? And the 3 points I listed here. The first point, the property is evaluated at the flow temperature, T sub infinity, except PR sub S. So there is a parameter PR sub S. That's a Prandtl number evaluated at the surface temperature. So don't confuse PR sub S with the surface Prandtl number. There is no definition for the surface Prandtl number. Surface is a solid. Prandtl number is the property of fluid. The PR sub S just emphasize the Prandtl number is evaluated at the surface temperature. So sub S indicate the temperature has to be the surface temperature. Okay? So that's how we evaluate the fluid property. The second point is the limitation. It's require the Prandtl number to fall into this range, 0.7 and 500, as well as the Reynolds number to be less than 10 to 6. The third point is the Prandtl number, the little n, we know it should be close to 1/3. For many correlations, they use 1/3. But for this specific correlation, he insists using different correlation based on the Prandtl number. For Prandtl number equal to 10 or above, n is equal to 0.36. Otherwise, it's 0.36. Now, they are very close, so I don't expect a big difference between these two. And if you think about it, 1/3 is about 0.33, right? So 1/3 is about 0.33. So these two n are very much close to 1/3. So that's the second correlation. The last correlation for cross flow of a cylinder is called Churchill and Brainstem correlation, and it's applicable to the product of Reynolds number and Prandtl number to be greater or equal to 0.2. It's much more complicated, but it has been, it was developed much recently, so I assume it has a better accuracy. And for this correlation, the flow property is evaluated at the film temperature. So that's for a cross flow of a circular tube or circular cylinder. And we will have a few examples later on. But if for the case of non-circular cylinders, we only have one correlation. That's a helped equation. The helped equation, it takes exactly the same form as for the case of a circular cylinder. So it's a constant C multiply Reynolds number to M multiply Prandtl number to 1/3. Property chosen at the film temperature. And for non-circular cylinder, we have to rely on table 7.3 to find the constant C and constant M. And it depends on the shape of the cylinder, whether it's a square cross-section or other type of cross-section. And also for each cross-section, the flow direction will affect the heat transfer. So you see, for the square cross-section, it lists two type of flow directions. So one is flow perpendicular to diagonal. So this is a diagonal. Okay? The other is flow perpendicular to the side surface, and they have different constant C and M. Okay, so you have to pick which flow direction. So not only the cross-section configuration, you also need to know what's the flow direction. Okay? And if you have something between, then you probably have to interpolate between these two. The other point I want to make is when you choose a kinetic length for flow of an object, so let's say this is some object. Okay, so this is the object. Doesn't need to be a spherical. It can be any object. Okay, so let me draw something. Let's say that's a typical object, and we have a flow over this object. How do you select the kinetic length when you compute the Reynolds number? The Reynolds number is equal to U of the flow multiply some reference length divided by the flow viscosity. So how do you choose this reference length? We choose the length that is perpendicular to the flow direction. So that's the reference length we choose. Okay? So I assume this has been taught in fluid mechanics. Okay, so that's that's exactly what we do here. So for diagonal case, we choose the diagonal as a reference length. For this flow direction, we choose the side length as a reference length. Okay. So now we can, we can work together for one example related to flow of a cylinder, both circular cylinder and a non-circular cylinder. Okay. So I break it into three cases. Case A, a long circular cylinder or long circular tube. Okay. So that's this is a top view, a cross-section view. Flow velocity 15 meters per second, temperature 25. The surface of the cylinder has a high temperature at 75 Celsius. Now we assume the diameter is 1 centimeter. It's a long cylinder, and we want to determine the average heat transfer coefficient as well as the heat transfer rate per unit length. Okay. And let's start with the first correlation, the Helpert correlation. Okay. So we use Helpert correlation to find the H. For this type of calculation, the first thing you need to do is to find the thermal property. Since we plan to use the Helpert equation, the property had to be evaluated at the film temperature. So this is a table which is the thermal property of gas. In our case, that's air. So this is a table for the property which you can find it at the appendix of the textbook. Okay. So our plan is to use the Helpert equation. So we have to evaluate the property at the film temperature. So let me calculate the film temperature. So let me stop the view this so I can. Okay. So film temperature in this case is 1/2 of the surface temperature, which is 25 Celsius. And the flow temperature, surface temperature actually is 75. The flow temperature is 25. So take an average, that's 50 Celsius. But if you look at the table, it's based on the temperature in Kelvin. So we have to convert Celsius to Kelvin by adding 270. So T flow equal to 50 plus 273 Kelvin, and turn out to be 323 Kelvin. Okay. And 323, it's about the midpoint of 300 350. So the midpoint is 325. So we have 323. So it's particular. So it should be the average between these two law. Okay. And we need to find the Reynolds number, and the Reynolds number requires the viscosity. So viscosity, we look at this column. So it should be between these two numbers. I did the interpolation. So it turned out to be 18.5. Okay. So mu equal to 18.5. Is that correct? No. Be very careful. This 18.5 is mu multiplied 10 to 6. And then you get 18.5. So the actual viscosity has to be 18.5 multiplied 10 to minus 6 with the unit of meter square per second. Okay? So these are the things you need to pay attention. So it's multiply 10 to minus 6. Okay, so I did calculation here. So I found these thermal property based on the film temperature. And then we can proceed to find the Reynolds number. And for circular cylinder, as I said, we choose the diameter as the reference length. Diameter is 0.01 meter. Okay? So that's That's why I put 0.01. And the final random number is 8,108. So now we can go to table 7.2 to look up the value of C and M. So random number 8,000 is fall into this column. Okay, so we pick C equal to 0.1993, M equal to 0.618. So we can find C. The table 7.2 give us C equal to 0.193. Yeah. And M equal to 0.608. So the natural number based on the diameter, and it had to be average, okay, equal to C multiply random number of M multiply random number 1/3. That's a helped equation. So we just plug in all those numbers into this equation, and we find the natural number to be 44.8. It's a dimensionless number, so it doesn't have a unit. Okay? And the H average equal to the natural number average multiply K divided by D. And the K had to be K of the air. So we have to find the thermal conductivity of the air at the mean temperature, at the film temperature. So you have to go to this table to find the K. Okay. Sorry. And after you put all these numbers into the equation, the K turned out to be 125. It does have a unit, watt per meter square per Kelvin. So that's the H. Now we can, compute the heat transfer rate per unit length. It's H. You can think it this way: Q equal to H multiply area multiply delta T. So H is the H we have found. The area, it's per unit length. So the area had to be the side surface area, pi d multiply L, but the L, L is equal to 1 because we need a 1 unit. Okay, so that's the area. Multiply delta T, which is T surface minus T infinity. Okay. So, this equation, the important part is how do you choose the area? Okay. So circumference multiply the length. Since we need a per unit length, we make length equal to 1. And equal to 196, and unit had to be watt per meter. Okay. So that's a very simple calculation. Now, I also tried the second coordination, the Zukowski's equation. And for this coordination, the property is evaluated at T sub infinity, the fluid temperature. Okay. And I did the calculation, it turned out to be 50.4 compared to the helped equation, the result from helped coordination. This is about 45, and here is about 50. So it's about, the difference is about 5. 5 divided by 50, that's about 10% difference. Okay, so this is something we expect for this correlation. The error involved is typically around 10, or sometimes it can be as high as 20%. Okay, so so when you design something using this correlation, you really have to make sure to have a safe factor with the expect, to anticipate the 10% to 20% error by deducting the safety factor. Okay. Now move to the case B, when I have a square cross-secking tube. So now the cross-secking is a square. The flow is perpendicular to the side surface. For this case, we compute the random number based on the reference length, which happened to be the side length equal to 1 centimeter. Okay, That's why we have the same Reynolds number, because the reference length is the same as the circular cylinder. We have the same reference length, result the same Reynolds number. And based on this Reynolds number, we go to a different table. This time, the table had to be the 7.3 for non-circular cylinders. Okay, and since flow is perpendicular to the side surface, so we pick up this configuration, and the Reynolds number is within this range. So C is equal to 0.158, M equal to 0.66. And we plug into this helper equation, do the calculation, and here is the final result for the Nusselt number. And for the H, we use the same relationship. I found H equal to 149. So now move to the last part of the question. Find the heat transfer rate per unit length. So equal to H multiply the area. How do we pick the area? I mentioned this is a part where you may make a mistake. So how do we choose the area? What is the area we should put here? We're looking at a tube with a cross section, with a square cross section. So the area, if this is 1 unit, L equal to 1, we are talking about all the side surface area. Okay, so this area, so all the side surfaces. So it's 4 multiplied d, because each side has a length of d. 4d multiplied 1. 1 is because we need a unit. Okay, so the area is 4d multiplied 1. For circular cylinder, it's a pi d, but for square cross-section cylinder, it's a 4d. Multiply Ts minus T. The rest is, quite straightforward. And I did the math, and I found Q prime equal to about 300 watt per meter. So that's my Q prime. Now the last case, case C, it's a square cross-section tube, but this time I let flow perpendicular to the diagonal. So that's a diagonal. Okay? In this case, we will have to choose a different reference length. This has to be our reference length. The side length A equal to 1 centimeter. The reference length D will be equal to square root of 2 multiply A. Okay, I assume you know this relationship. Okay, so D equal to square root 2 multiply A. So when you compute the Reynolds number, the D had to be square root 2 multiply 0.01. A equal to 0.01, 1 centimeter, divided by mu. Okay, and equal to, now U infinity multiply 0.01 divided by mu, we now it's equal to 8,108. So we have to multiply additional square root of 2, which is square root 2 equal to 1.41. Okay, 1.414. So, and it turned out to be a little higher than 8,000, equal to 11,466. Okay, and then we go to table 7.3, but this time we're looking at this configuration. So we pick these two for the help equation. So I found Cm, and then use the help equation. I found the H, and from H I can find the heat transfer rate. Okay, so quite simple. But if you compare the heat transfer rate for case B and case C, you will see an increase in heat transfer rate when you change the flow direction. Okay, so for case B, when you have this type of flow direction, flow is perpendicular to the side surface, the heat transfer rate per unit length is 300. But when you change the orientation of the tube, make flow perpendicular to the diagonal, you are able to increase the heat transfer rate. Okay? By a small change of orientation, you are able to increase the heat transfer rate by about 20%, compared to 300. This is, a little above 20% increase. Okay. Now, can we explain why we are able to increase the heat transfer rate for this configuration? Okay. Now, this can be actually explained based on the fluid mechanics. So if we look at the fluid behind the cylinder, for case B, the weak region, so that's a weak region, is much narrower or smaller compared to case C. Case C, you see, you have a larger weak region. Okay, and the case B, you relatively you have a smaller weak region. And the weak region, what's the characteristics of a weak region? If you have a weak region, what happened inside this weak region? The pressure is very small. Sometimes, quite often you can have a negative pressure. Okay, you have vacuum pressure. Okay? And the drag is due to the pressure difference. So for this case, you will have a high drag compared to this case because the pressure difference is higher compared to case B in case C. Okay, case C has a high drag than case B. So that's the fluid mechanics side. Now for the heat transfer part, if you look at the flow region, you have more surface area involved turbulence compared to case B. Case B, the surface area involved turbulence is smaller compared to case C, right? And we know turbulence promotes heat transfer. So when you have a larger area in contact with turbulent flow, we expect a higher heat transfer rate. Okay? So that's the explanation because we have a larger weak region in case C compared to case B. Okay? So that's why we have higher heat transfer rate between, for case C, we have this, conclusion. Okay. Okay, so the last configuration we will cover is flow over a sphere. Flow still the velocity you use sub-infinity, temperature T sub-infinity. The square has a diameter of D, and it doesn't matter what direction flow goes, because the part of, the sphere is isotropic. It has no preferred direction. So that's why we don't need to specify, whether the flow is cross flow or not. Okay, it's flow over sphere, as simple as that. Okay? And there are two correlations based on the type of sphere we are dealing with. If you have a solid sphere, okay, if you have a solid sphere such as a marble, okay, we use a vertical correlation. So that's a vertical correlation. And the property is evaluated at the fluid temperature, T sub infinity. So for this correlation, the fluid property are evaluated at T sub infinity, except mu sub s. So that's a viscosity evaluated at the surface temperature. Okay. So this is for a solid sphere. Also, the limitation is given by in terms of Prandtl number and Reynolds number and viscosity ratio. So there are a few limitations for this correlation. If you, if your case doesn't belong to the, doesn't fall into this range, then you have to do, you have to do more your own research or try to find a different correlation from the literature. Okay. So that's a case of a solid sphere. Another situation is when you have a liquid droplet. So when you have a droplet, such as a water droplet, fall in air, or a water droplet fall in oil. Okay? In that case, we have the Lorentz-Marshall equation. Okay. So that's a Lorentz-Marshall equation, which is for a liquid droplet. And the flow property is evaluated at film temperature. Okay. So two correlation for different applications. The first one, the vertical correlation is for a solid sphere. The second one, the Lorentz-Marshall correlation is for a droplet. Okay. And the property are evaluated at different temperature. One is at the T sub infinity, the other is at the T sub F, which is the film temperature. I prepared two examples. The first example is to explain why these two correlations, if you pay attention to these two correlations, when random number reduced to zero, when flow velocity becomes very small, random number can be neglected, the natural number reduced to 2. And here the same thing, when random number reduced to 0, then natural number will become 2. So why natural number equal to 2 when flow velocity is extremely small, random number reduced to 0? Okay. So that's something related to stock flow or clipping flow. So when flow moves very slowly, that's how we call it clipping flow. And we can define the flow based on the random number. So we say when the random number is much smaller than 1, the flow is called stock flow or clipping flow. And the drag, so we have a sphere with diameter of d, a flow slowly passing this sphere. The drag can be determined by the stock drag, 3 pi multiply mu of the flow multiply u of the flow velocity multiply the diameter of the sphere. So that's a stock drag. And even though it was derived based on the stock flow assumption, very low random number assumption, but actually this stock flow drag is still applicable to random number as high as 5. So when random number is 1 or 2 or up to 5, this still provides a good estimate to the drag on the sphere. Okay? So that's what we learn in fluid mechanics. It's very important. Okay? And you will see in the next example, we will need this stock drag to determine the flow velocity or the particle velocity. So now, but for us, we want to derive, and this condition, when flow is very slow, convection can be neglected, conduction dominate, and the natural number will reduce to 2. So why natural number equal to 2 when you have a conduction dominate situation? Okay. So let's look at the configuration here. So here we have a sphere, diameter is d, so the radius, let's call that r1. R1 equal to half of the diameter, right? And it's placed in a larger flow. And I imagine there is a spherical surface far away from the sphere with the radius equal to R2, but R2 is much larger than R1. So we even can claim R2 is approach to infinity because we are looking at isolate sphere in a larger fluid, okay? And this is a spherical surface. Now we are looking at the heat transfer between these two surfaces, okay? The surface of the sphere and the surface of an imaginary fluid, which has a temperature T sub infinity. And the heat transfer rate between these two surfaces equal to delta T divided by the thermal resistance of conduction. So for the spherical wall, the conduction resistance is 1 over R1 divided by 1 over R2, and then whole thing divided by 4 pi over K of the fluid. Okay? The K is the K of fluid. And R2 approach to infinity, this term reduced to 0. So Q will be equal to Ts minus T infinity 1 over R1 minus 0, 4 pi K. And we rearrange it. So we move 4 pi K to the numerator. So we have 4 pi K 1 over R1. We flip it to the numerator. So you multiply R1, which is half of the diameter. Okay, multiply temperature difference. So that's a heat transfer rate between the surface of the sphere and the fluid, and equal to 2 pi K multiply diameter multiply temperature difference. So that's a Q. But if we use a different equation for Q, we use Q equal to H convection coefficient multiply the area of the sphere, which is pi d squared, multiply Ts minus T infinity. Now this is a more general equation which relates Q with H. Okay? So we compare these two equations. We find H bar multiply pi d squared has to be equal to 2 pi K multiply d. Okay? So the first equation is based on the conduction between the surface of the sphere and the outside fluid. The second equation is using the convection formula. Okay? So now we have H bar equal to pi cancel out d. We can cancel out 1 d. So H bar equal to 2k over d. So let me write it. So H bar equal to 2 multiply k over d. But H can be related to natural number by natural number multiply k over d. Okay? So that's the definition of H. So compare these two equations, we find natural number has to be equal to 2. Okay? So even though, conduction is not convection, but there is a dimension is convection coefficient when conduction dominates, and that's a natural number, and that natural number is equal to 2. Okay? So you can consider conduction as a special case of convection where natural number equal to 2. Okay? So using natural number equal to 2, you find the H bar, and then you can determine Q. And the result will be the same as you find using the conduction equation. Okay? So that's a simple derivation why the natural number equal to 2 when we have a conduction situation. Okay, and this also explains the two correlation reduced, the natural number reduced to 2 when Reynolds number becomes 0. Okay, so now I have one more example. This is the last example, but this example is quite involved. Okay, so let's see if we can finish this example before 1240. So here we have an electrical circuitry is written onto a photovoltaic panel. So this is a photovoltaic panel. And this is a thermal inkjet printer. So we deposit a stream of a small droplet from a thermal printer. So these are a stream of droplet being deposited onto a photovoltaic panels. When the droplet leaves the ink or leaves the printer, the temperature, we call it initial temperature, is 200 Celsius. It had to be high because remember it had to be liquid. It had to be liquid, and when it strikes onto the surface of the photovoltaic panel, it becomes solid. Okay, at 50 Celsius, we expect it. It becomes solid. So initially it's a liquid at a high temperature of 200. Let's continue with the statement. It is desirable for them to strike the panel at a temperature T sub final equal to 50 Celsius, and the surrounding air temperature is equal to 25. And the droplet are ejected from the plinth head, so the droplet being ejected at their terminal velocity. Okay? So that's something we define in the fluid mechanics, terminal velocity, okay? U sub T. So the droplet move at a terminal velocity. Usually, it's when the droplet leaves the plinth, the velocity is 0, and quickly it reaches to the terminal velocity. But according to the statement here, we can assume the droplet has a velocity equal to terminal velocity at any time instant. Okay, we neglect the transient period. Determine the required standoff distance L. So we want to determine this L such that the temperature when the temperature of droplet equal to 50 when it strikes onto the surface. Okay, so when L is too smaller, then the droplet will have a high temperature when it strikes onto the surface. When L is larger, the droplet will have a low temperature. If L is sufficiently long, eventually the droplet will reach a temperature equal to 25, the ambient temperature. Okay? So L will determine the temperature of the droplet when it strikes onto the surface. Okay? So pretty complicated problem, but we can break it into a few small questions. The first question is, how L is related to the velocity and the time? So we know for a droplet to fall from the ink printer to the surface, if the time is t, the velocity is u terminal velocity, u sub t, then that's a relationship. That's the equation for us to find the L. L is the one we want to find. But looking at this equation, we don't know t. We don't know u sub t. That's the terminal velocity. We don't know L, right? So the first thing we need to do is to find the terminal velocity. So that's step one. Find u sub t. Okay, and that can be done based on the force balance. Now this part belongs to fluid mechanics. I assume you know how to find the terminal velocity. So that's one question we need to answer. What's the terminal velocity of the droplet? The second question is, how do we find the time t? Find, as I said, t will control the temperature of the final temperature. If you have a longer t, then the temperature at the final will be smaller. Okay? So this is a transient conduction problem with respect to the droplet. Droplet initially had a temperature of 200, and finally its temperature became 50. That's a transient conduction problem, and the time will control the temperature. So if we know the temperature, then we can determine the time. In some other situation, if we know the time, we can determine the final temperature. But for our example here, we know the final temperature, so we should be able to determine the time. And that's where we learned in chapter 5. So this example really combine, chapter 5 as well as chapter 6 and 7. So from chapter 5, the transient conduction problem, we compute the Biot number based on the catalytic length. So let me remind you how to calculate the Biot number. based on the characteristic length, is equal to h multiply L sub c over k of the droplet, and L sub c for a spherical particle, L sub c is 1/6 of the diameter, okay? And h is unknown. So if we know h, then we can find the Bill number. We expect the Bill number to be very small because the droplet has a very small size. And we, as for small Bill number, we can use the lumped heat capacitance method. Theta over theta I equal to E2 minus T over tau. That's a solution of the lumped heat capacitance method. Okay, LHC is its abbreviation. So, and in this case, theta is T final, which is 50, minus T infinity, which is 25. That's the ambient temperature. T initial, which is 200 minus 25, equal to E2 minus T over tau. And the tau is the time constant equal to rho multiply C multiply volume of the droplet. I use sub D to emphasize droplet divided by H multiply A sub S. And V over A sub S is the characteristic length. So eventually we can replace V over S by 1/6D over H. Okay. So again, we need the H. So once we have H, we can find the time constant, and from time constant, we can find the T. So that, that's for the step 2. We should go this route to find the time T, okay, using the LHC method. And so now everything end up with H. We stuck at H. We don't have H. So that's where we have to answer this, the third question. What's the H value? Okay. So let me, instead of using step, I using question 3. Okay. Because when we talk about step, we always start with step 1, then move to step 2, step 3. But in this case, we actually have to start with a question 3 first. We need to find the H before we can find the time, right? So that's why I changed step to question. So question 3 is, how do we find the average convection heat transfer coefficient? H equal to Nusselt number multiply K of the droplet, my bad, K of the fluid. So this is where you easily can make mistake. K of the air, when we compute the convection, it's about the fluid property, okay? Divided by the diameter of the sphere. And the Nusselt number, this is the case for a droplet. So Nusselt number can be found using the Marshall correlation, which is equal to 2 plus 0.6 Reynolds number of 1, I believe 1/4, Prandtl number 1/3. Okay, so let me double check. I did some research in this area, so I'm pretty familiar to these correlations. Okay, let me see. I have, 1/2, not 1/4. My bad. So 1/2. So that's how we find the H value. So if you look at this equation, we need to find the Reynolds number, T. Okay. So now we have a pretty good idea how to solve this example. Step 1, that's where the question 3 is being answered. We compute the Reynolds number, and from the Reynolds number, we determine the Nusselt number. From Nusselt number, we find the convection coefficient H. Okay, that's step 1. So it turns out this is step 1, the first step. Okay, we find the H value. Step 2, actually, in order to find the Reynolds number, what's missing here? What's missing? terminal velocity. So this cannot be first step. The first step actually is to find the terminal velocity. Okay. So let me take back what I said. Okay, so this is step one, find the terminal velocity. Because in order to calculate the Reynolds number, we have to know the terminal velocity. And step two, find the H value. And step three, find the time it required. Okay, find the t. And the final step, now we can, so we are in a position to find the length, which equal to the terminal velocity multiplied the time t. Okay, so that's a process. Now I already solved this problem, so since I only have 4 minutes left, so I will, just show you the details of the calculation. Okay. To find the terminal velocity, the first step, to find the terminal velocity, we use the force balance equation. Okay, so this is a sphere. The force acting on the sphere include the drag, which is the density of the droplet multiplied the volume of the droplet. V sub d is the volume of the droplet. Multiply g, that's the weight of the gravity force. Okay, so that's the force pointing downward. The force pointing upward is the buoyancy force, equal to density of the air multiply volume of the droplet multiply gravitational acceleration constant g, plus the drag. The drag is also opposite to the flow direction, so it's pointing upward. And we assume the flow has a low Reynolds number, so the stock drag is applicable. So we use a stock drag. Okay? And then if you apply the force balance at the terminal velocity, terminal velocity means the particle no longer accelerate. So acceleration equal to 0, all the force has to be balanced. Okay, so the drag 3 pi mu of the air multiply diameter multiply the terminal velocity, that's a stock drag, has to be equal to the weight, which is low of the droplet, multiply volume of the droplet, multiply g. So that's the weight. If we use the notation W for the weight, F sub d for the drag, weight minus the buoyancy force, which is density of air multiply volume of the droplet multiply g. So that's the buoyancy force B. Okay. And these two can be further simplified by taking out the common factor. And the Vd is the volume, which equal to 1/6 pi multiplied d to cube. Okay, that's a V sub d. So we have all these values. And the only unknown is U sub t, that's the terminal velocity. That's how we find the terminal velocity, using the force balance equation. So here is what I did. So I assume the Reynolds number is small, so I use the stock drag, and to find the terminal velocity, turn out to be 0.19 meter per second. And since I make an assumption, so I need to check the assumption by calculating the Reynolds number, which turn out to be 0.5 is less than 1. So the stock flow assumption is good, is okay. So the stock drag is fine. And based on this Reynolds number, we can determine the Nusselt number. So this is the Rank-Marshall equation, and I find the Nusselt number, and then I can find the convection coefficient H value. And based on the H value, now we can determine the Biot number. As expected, it's very small, much smaller than 1, so we can use the lumped heat capacitance method. Okay, and I find the T equal to 1.9 multiply a time constant tau. The time constant tau equal to about 0.016 second. So now I have t equal to 0.03 second. Okay, so that's how we find the t. Now the final step is just combine use of t, the terminal velocity, and the time we have found, and the final result for the L is about 5.8 millimeter, so about 6 millimeter. Okay, so this is a very interesting example, and I think you should be proud of yourself because now we are in a stage that can do these complex design problems, right? So with that, I will conclude today's lecture, and you guys can start today's in-class quiz. Yes, thank you.